Good morning, everyone. Why don't we get started? Well, good morning. It's very nice to see everyone. My name is Ed Blucher. I'm the director of the Enrico Fermi Institute. I'm very happy to welcome you to this year's Compton lectures. The Fermi Institute has hosted these lectures. This is the 92nd in the series, and we've hosted them since 1972. So the first one, Van will remember, the first lectures were given by Bruce Winstein. So there's a long history of outstanding young physicists, young scientists who've given these lectures, who many of them have stayed at the university and many have gone on to other places. So it's a really great opportunity for us to hear about exciting things in science from some of the future leaders in these fields. So I'm pleased to introduce this year's lecturer, Philipp Windischhofer. He was an undergraduate in Vienna at the Vienna University of Technology. He then did a dual master's degree at ETH in Zurich and École Polytechnique in Paris. And then he moved to the University of Oxford to do his doctorate. And since 2022, he's been a Granger Fellow here at the University of Chicago. And I think you'll find that the series that he's going to go through for you, discussing interplay between technology and science in both directions, I think is really going to be fascinating. So I think you have a wonderful series in store. I wanted to mention a couple of other things before we get started. One is to introduce one other person who's back in the booth, who many of you have met, Mary Heinz. She's the operations manager for the Fermi Institute and makes sure that everything here runs smoothly. I should also thank many of you. The lectures are being recorded and posted, so you can look at videos afterwards if you want to look back at things or if you miss one of the lectures. And we're able to do that because of some very generous gifts from some of you attending, so thank you. That's very much appreciated. If you're not on the email list for the Compton lectures and you'd like to be added, Mary's email address is up on the board, and you can send her an email and she'll take care of it. So I think that's everything I wanted to say, so enjoy the lectures.
Okay, thanks very much, Ed. Thanks very much, everybody, for coming.
It needs to be louder.
Needs to be louder. Can we have it louder, Mary?
Very loud.
Is it getting louder?
Yes.
Is it fine like this? A bit more. Okay, maybe I can just shout. Is it better like that? I have it all the way up. Fine? Okay, let's see. Let's just get started, and then please interrupt me if you can't hear what I'm saying. Welcome, everybody. I want to tell you a story in these 8 lectures. And it's very much a story about what happens when we go up and we open our eyes and we look out into the world and we look out into the universe. And we're going to see what the universe is like, the beauty and the diversity of the universe. But it's also a story about, if you look carefully enough, you see a lot of complexity. And a lot of complexity means a lot of confusion some of the times. But then it's also a story of how, if you stare at the complexity for long enough, suddenly everything starts to make sense, and you start to understand what's going on in the universe. And once you begin to understand what's going on, the entire character of the story changes. Because once you understand what's going on, you can start to influence things, and you can start to make the universe do what you want. And that is the world that we live in today. If you open your eyes on a nice Saturday morning at Millennium Park, this is what you might see. Technology is everywhere around us. I found about 8 people in this picture using their cell phones, either to call somebody or to take a picture or to check something on their inboxes. There is electric lights that shine onto the monument here at Millennium Park. There's elevators that take us upstairs to the top floors of these tall buildings. If you look at the reflection, there is radio antennas on some of the surrounding buildings that work with the cell phones to make sure that we actually can call somebody. And of course, people live in their apartments that are wonderfully air-conditioned so they don't get too hot. And obviously, these buildings, they also have electric lighting. So technology is truly everywhere around us, and we can't really escape it. But it wasn't always like that. If you look back to ancient Greece, people didn't have cell phones to call somebody. Instead, they had people like these. They were called day runners, and they would literally do exactly what the name says. They would run for a day to transport important messages. And they would be able, let's say, to run around 60 miles in a day if you stretch it. And they would be able to deliver that message. These were very athletic people. This was literally their job, to run and to transport messages. Couriers, if you want to call them. But then, ask the question, why didn't the ancient Greek have radio? Why couldn't they simply tune into their station to see what was the outcome of this or that important battle that was going on in some neighboring city-state? Why did they have to wait until the next day or the next 2 days until the day runner could come by to inform them what has transpired? So why didn't they have radio? And today, obviously, we can just go and ask a computer what it would have been like if they did indeed have radios to listen to in ancient Greece. And this is exactly what I did here. Okay, so here is the radio. And here is people in ancient Greece, dressed like people were dressed in ancient Greece, listening to their radio. But obviously this was not the case. So why didn't they have radio? And if you look about what the ancient Greeks were able to do, they were able to do wonderful things. Here is a golden bracelet, and you can see it's got very fine gold wire all wound around it. Extremely intricate, extremely difficult to make, and wonderfully beautiful. They were also able to craft metal. So here's a water vessel from the 7th century BC, made out of bronze, that they could make. And then even in the 2nd century BC, they could make glass. So here's, again, a glass amphora that could hold water or perfume or any very expensive substance. And obviously it wasn't as nice and shiny and transparent as modern day glasses today, but it was glass nonetheless. And then if you look at what the first radio transmitters and radio devices used, they would be powered by something like this. It's called an induction coil. And it's nothing but, in this case, a pile of wood and wire wound around it. The first radio receivers would be nothing but a bunch of metal balls stacked on top of one another in a glass tube. Even the first radios would run on electricity. And the first reliable way of generating electricity would literally be just a glass ball that would be spinning on a rod of wood. So if the ancient Greeks could build these wonderfully intricate gold wire bracelets, why couldn't they also have built an induction coil? It's just wire wound around something else. If the ancient Greeks could build these wonderfully beautiful and intricate metal vessels, why couldn't they also just build a bunch of metal balls and stack them on top of one another? And if they could build glass, wonderfully intricate glass amphoras, why couldn't they simply build a glass sphere and turn it so they could generate electricity? So now the question of why the ancient Greeks didn't have radio suddenly is sort of not obvious anymore, right? Why didn't they think about doing any of those things and putting it together to make a radio? Would have been so much easier if it could have been a long-distance radio link between Athens and the other city-states to talk to each other, to coordinate during warfare. But they didn't. And so this is very much going to be the theme that runs through these entire series of lectures. Today we have all of those things. Today we have cell phones, and today we have electric lights and elevators and air conditioning and so forth, but the ancient Greeks didn't. So something must have changed between then and now to make this happen. But what was that? That's the question. And these 8 lectures are going to be the answer, my personal answer to that question. And it's going to be a story about fundamental science as a way of looking at the world, a way of appreciating the chaos and diversity that we see in the world, and how then we can turn that knowledge about the world around into technology, and we can begin to change the world. So this is going to be very much a story of invention, but also a story of discovery. We are going to look at how some of the more important scientific discoveries came about throughout histories, throughout centuries. How did people figure out that if you rub a glass ball, you could generate electricity? how did people figure out that if you run wires in a coil around a wooden pole, you could generate radio waves? It wasn't obvious. It wasn't certainly obvious because the ancient Greeks didn't do it. So how did the first person, decide to do it? And how did these discoveries pave the way for technological progress? And how did that progress in the end shape the world that we live in today? So how on earth did we get from a golden, wonderfully shiny bracelet in ancient Greeks to induction coils that finally give us radio? How on earth was that story possible? Now that's going to be a fascinating and long-winded story. Sometimes it's going to be chaotic. Sometimes many things are going to happen in parallel. Sometimes sheer luck intervenes to put people on the right path. And this is why we're going to have all of the next 7 lectures to talk about it. But this is also why, in the first one today, I don't want to dive into the details of history just now, but I want to give you the bird's eye view. And if we want to understand how we got here, we first need to appreciate where we are at today in our wonderfully modern world. So where are we now? This is very much going to be the question for today. And then, once we roughly understand where we are now, how did we roughly get there? Are there some commonalities in that trajectory that brought us to our current place that we could point out and that will guide us as we go along in the next 7 lectures? So how did we roughly get here? That's also a question I want to answer for you today. And then next week, next Saturday, the real story is going to begin. We're going to go back to ancient Greece, and we're going to follow how people really went from golden bracelets to radio transmitters. So let's go. Let's get a taste for what kind of technology we have today. Let's get a taste for why we have cell phones and elevators and air conditioning and electric lighting. All of these things have in common that they run on electricity. But where does the electricity come from? If you open your TV remote control, or if I open my clicker here, you would find a battery like this. And you could say, well, stupid question, this is where electricity is coming from. My computer right here is plugged into the outlet to charge it. And I could say, well, stupid question again, this is where electricity is coming from. But right away, you will be able to point out that there is a difference between these two sources of electricity. Indeed, the battery here is self-contained. It doesn't require anything external to it to keep the device powered up. On the other hand, your wall outlet, when you move into your apartment, you will have to call ComEd to turn on the electricity. So right away, this tells you that while that battery here is really self-contained and therefore contains some electricity that it's providing to you, the wall outlet is not self-contained in the same sense. It's not a source of electricity. It still delivers electricity, but it doesn't produce that electricity on its own. Instead, if you open up that wall outlet, you would find 2 wires connected to the 2 pins. So then you say, aha, obviously, if the electricity is not generated in here, maybe it's generated on whatever is on the other side of these 2 wires. So you start to follow where these wires go. And if you do that, you probably would walk outside your house and you would see something like this. You would see the 2 wires from your house going into that big box on that wooden pole, and that's called a transformer. And it's called that because what it does is to transform the electricity that you need in your house into electricity that can be more easily transported over longer distances. And this is why the color now changes from red to blue. And then you say, okay, fine. That transformer apparently doesn't also produce the electricity because it's still got wires coming out the other side of it. So whatever does give me the electricity is probably on the other side of those 2 blue wires, those 3 blue wires. So let's follow where these blue wires go. And as you keep going, you start to go into the suburbs, and eventually you will start to leave Chicago. And those power lines, they will get bigger and bigger and bigger. But there would still be 3 of them. And eventually they would sit on top of these wonderfully big metal masts that would carry it along many hundreds of miles in some cases. And as you keep going, at some point, you might end up at a power station. And since we're in Illinois, you might up at Byron Generating Station, which is just south of Rockford, Illinois. And there's the wires. And you might see that these wires go into this big elongated building here. And you see, aha, obviously what's inside the building is somehow the source of electricity. So let's go inside that building and see what's happening. And if you enter that big hole there, you might see something like this. You would see the wires go into that big yellow machine here in the foreground. And if you ask somebody what that machine was called, they would tell you it's called a generator. And you say, aha, finally, if it's called a generator, maybe it's called that because it generates electricity. And you're already sort of excited because you might have found the end of your journey. So what's happening inside that generator that actually gives you the electricity? If you open up that generator, you would find the following. You would see your two wires that come in, and they would sort of be wound up in a coil, in a spiral, and in front of that spiral you would find a magnet that would rotate. It's a magnet just like the one you might have on your fridge that sticks to metal, but in this case it doesn't stick to anything, it's made to spin. And it's spinning in front of that coil. But the marvelous thing is, the wires are not connected to anything. You see, the one wire is coming in, it just wraps around and goes back out. It's not as if what you wanted to find probably is, these wires, they're connected to something and that something is generating the electricity. That's not at all what happens. These wires come in and they wound around and then they come back out. So how on earth does the electricity get into the wires if they're not connected to anything? Now maybe some of you who have heard this story before will just say, oh, electromagnetic induction and so on and so forth. But I just wanted you to appreciate how absolutely marvelous that thing is. There is somehow the electricity is getting into the wire, but it's certainly not because the wire is touching something. Right? The electricity is getting into the wire through the air in some mysterious way. And something must have to do with the magnets. But what does a magnet have to do with electricity? How does a fridge magnet that sticks to your fridge, if you spin it, power your hairdryer? Right? It's not clear. It's not obvious. Here's that spinning magnet. So now we know what's at the end of these two wires that end right here in the wall outlet. There is nothing but a coil, a spiral of wires, and a turning magnet in front of it. But then, if I look at my charger, and you look at what's written in very small letters, on the charger, you might see something like this. It might say 120V 60HZ. What does that mean? Well, HZ stands for hertz. That's a unit, like meters. And while meters measures length, hertz is a unit that measures time, or frequency, if you want to call it. And 60 hertz means nothing else other than the electricity between these two wires oscillating 60 times a second. Okay? Something like this. And that happens because that magnet in a power station far away rotates 60 times a second. And if you were to measure very carefully how that electricity looked between your two outlets on the wall, you would see that it does something like this. It goes up and down 60 times a second. The V here in 120V means volts, and that's another unit. And it's a unit that somehow measures the strength of the electricity. Okay, so in this case, 120 volts means some sort of average of that oscillating electricity. Electricity goes up and it goes down, but on average, it's at 120 volts. Now we can see volts written somewhere else. If you look very carefully at your battery, you might see that it has written on it in tiny letters 1.5 volts. That tells you that the electricity that comes out of your battery must be somehow related to the electricity that comes out of your wall outlet because they use the same units. But clearly that battery is less powerful than your wall outlet by about 80 times. And in fact, if then you ask the question of where does the electricity in my battery come from, is there a tiny spinning magnet inside? And you open it up and you find none of that. There's no tiny spinning magnet inside. Instead, you open it up and you would find something like this. It's like some metal foil and some gray goo that's somehow sprayed on that metal foil that's sticky and it's sort of kind of wet. And apparently this generates electricity. That's a lot weaker but it's still electricity. So no spinning magnets. And in fact, if you were to measure again, you would also find that this is now a different kind of electricity. It would be 1.5 volts all the time without any oscillations. So that's an important point, and let's keep it aside for now. There's different kinds of electricities, and they're generated apparently in different ways, but it's not clear yet how they're generated this way. So the answer I gave you of where the electricity came from that I'm using here in my wall outlet is, there's a power station somewhere, and it has a spinning magnet, and that spinning magnet passes in front of a coil of wire, and then, for some mysterious reason, that gives me the electricity. But then fine, and you come back at me and you say, okay, but what makes the magnet spin? And the answer, if you ask the engineers around, they would point you to this big blue object that's right behind the generator. And in fact, that's joined up with the generator by means of a shaft. So if that blue thing turns, also the generator will turn. And you say, what's that blue thing called? And they would say it's a steam turbine. And that's turning. And if you opened up the steam turbine, you would see something like this. It would be a bunch of fan-like objects that are arranged along this shaft, and they would tell you that they're blowing high pressure and extremely hot steam through those fans. And that's why the fans are turning. And that's why the generator is turning. And that's why you get the electricity. But then you say, okay, fine, where does the steam come from that makes the thing turn? And they would point you to the next building, and they would tell you, enter there, and you will find a large pool of water that might look something like this. And they would tell you, we boil the water, and this is where we get the steam. And then we take the steam to the turbine, and this is how it spins. And in fact, here you can see a few people maintaining that big bottle of water, if you want. And so it's actually turned off, and you can see no boiling water. But this is where the boiling would happen. But then you ask these two people, and you say, fine, but what do you do to make the water boil? Where do you get the heat from to make it boil? And they would point you to the thing that they're currently pulling out of that, big pool of water. And they would call it a fuel element. And in fact, there's more fuel elements inside that are not currently pulling out. Okay, so they're taking out one of those. And they would tell you it looks something like this. It's just some arrangement of very, very long, very, very thin metal wires. And each of those metal wires, they would call a fuel element. Okay, one of them. And then they would tell you, if you open up one of them, here you have that long silver tube, and you looked inside, what you would find is what they would call a fuel pellet. Okay, tiny little small black rocks. Okay, and you can hold them in your hand, like they. And they will tell you, we boil the water because the fuel elements get hot, and the fuel elements get hot because the fuel pellets inside them get hot. Right? But they're not answering the question, because what makes the fuel elements get hot in the beginning? And I would say, it's because the fuel elements get hot because there's atoms inside them that make up the material from which the fuel elements are built. And those atoms, sometimes, they can split apart. And those two parts of the atom that would fly apart with extraordinary velocity, they would get trapped inside the material. And then what happens? Something else gets liberated. A tiny yellow particle that's much smaller than the atom. It's called a neutron. And that neutron can wander off and find another atom in that same fuel pellet, and it can also make that other atom come apart. And what happens when these atoms come apart and they fly apart with these extreme velocities is you get friction. And that is very much like, you trying to warm your hands on a cold day, you also get friction, and that is what makes the fuel element get hot. Because it's not just one or two atoms that fly apart, but it's many, many atoms, which overall have that effect of warming up the fuel pellet. And so you would conclude that this is where the electricity is really coming from. You would have these fuel pellets with atoms flying apart at extreme velocities. They would generate heat through friction, just as you rubbing your hands on a cold winter's day. That is what makes these fuel pellets get hot. This is what makes the entire fuel element become warm. But because they're submerged in water, this is what makes the water go warm and eventually boil. And this is where the steam comes from that runs through the turbine and makes the turbine spin. And the turbine is what makes the generator spin. And inside the generator, you would have the magnet that spins in front of the coil. And because of that, you get electricity. And that electricity would go through the big overhead wires. It would go through the transformer into your house and finally come out of the wall outlet. Okay, this is where electricity comes from. Now let's have another look. Let's go back to Millennium Park. There's 8 people using cell phones in these pictures. How does a cell phone work? So what happens if there's Bob, who is in San Diego, on the far end of the country, and he wants to call his friend Elise, who is in London, on the other side of the globe almost. So what happens if Bob dials Elise's number? Well, Bob is fortunate enough to live in San Diego, where there's lots of cell phone towers around. And the cell phone tower, you will have for sure seen them, looks something like this. There's a big mast, and it's got antennas on it that if you magnify, you will see a whitish, elongated object here. It's all closed up so as to be resistant against weather. But Bob's cell phone, upon dialing Elise's number, will send out a radio signal that travels through the air to that cell phone tower. And it will encode Elise's number, and it will also encode what Bob is speaking into the microphone inside his cell phone. And then that cell phone tower will receive that signal and transmit it through a wire, across the country, across the continent, and across a transatlantic cable until it ends up in London, where there is another cell phone tower that then sends out a signal that reaches Elise's cell phone. But then you ask, maybe you can imagine that these signals travel through wires, and maybe you can even imagine that these signals travel through very, very long wires, just as we have power come to us through very, very long wires. But how on earth does this radio business work? How can I send something to a cell phone tower without having a wire connect me to it? What's happening? So where does the radio signal come from? And to answer that question, we need to open up a cell phone. Because, whatever is producing those radio signals, for sure it will be inside the cell phone, because that's what I'm using. And in fact, if you open up that cell phone and you look very, very closely at what is inside, you would find a small, tiny little element that you would have to hold with a pincer because it's so small. And that's called an antenna. And somebody who is well-versed in electronics would tell you that this is what is producing the radio waves. But in fact, you don't really believe them, because if you look at this very, very closely, that antenna is just another piece of thin wire that doesn't seem to be connected to anything else. So how on earth can you have a piece of wire that just ends give you a radio signal? It's one of those other weird instances where something seems to come across the air, just as that spinning magnet before that wasn't touching anything gave us some very tangible electricity in the wire. And in fact, if you try to pursue that question, and you try to go back at what the first antennas was that people built, you would come across an object that looks like this. In fact, here is a real photograph of it. It's just 2 wires. It's about 4 feet long, so much larger than these antennas that you can find in modern-day cell phones. And it would have 2 metal balls connected on either side, but again, in the middle, there would be a gap. It's connected to nothing. And then, if you could time travel back to the moments when people were experimenting and were building these kind of antennas, you could observe what they were doing. They would take 2 wires connected to those 2 in the middle, and then just run electricity through it. But if you ask them, what kind of electricity are you using, they would tell you, well, this is sort of a kind of very special electricity. It's almost like the one that you have in your wall outlet, except at the time there weren't any wall outlets. But it would oscillate back and forth a lot faster than you would have in your wall outlet. Okay, so one oscillation would take 1/1000th of a second, whereas one oscillation on that wall outlet would take 1/60th of a second. Okay, so this is not 60 hertz, but it's 1 billion hertz. Much, much faster. And they would tell you that yes, even if you don't believe us, this is exactly what happens. If you take this electricity at 1 billion hertz and you send it into that piece of wire that's not connected to anything, you would have radio waves come out the ends. And then those radio waves, they would travel across the room and you would be able to detect them. Except that they wouldn't call them radio waves because radios were not invented yet. So something strange is going on. Clearly, these two situations, your wall outlet and those antennas, have a lot in common. Both of them run on these oscillating electricities. We have 60 hertz in our wall outlet, and we have 1 billion hertz on the antenna. So there's clearly something that connects them, but it's also clearly very different, because you're used to the fact that if you have nothing plugged into your wall outlet, you're not consuming any electricity. Right? So if these two wires just end, because you didn't connect anything, then you will not consume anything, you don't have to pay anything. But here, you see, it's the exact same situation. You have two wires connected to something, but then it just ends. But yet, you have those radio waves come out the ends. So clearly, there's some power being consumed, and that power gets sent away to the distant cell phone tower. Something is different. What I just tried to answer these two questions, I had to tell you a lot about how the world works. And today we are fortunate enough to really know a lot about how the world works. Right? For example, we know today that electricity flows very, very easily through thin metal wires. And that's in fact why we can send electricity across very, very far distances from the power station all the way to us. We also know today that rapidly oscillating electricity gives us these radio waves, whereas electricity that oscillates more slowly doesn't. And in fact, today we can also turn that statement around. And we can say our modern world works because we know a lot about it. Imagine suddenly the electricity goes off in your house. There's a storm or something. And it stays off for a couple of hours, and it's maybe a bit inconvenient because your fridge stops working, your computer stops working, you can't do anything, the TV doesn't work, it's dark. But after a few hours, the electricity comes back up because the engineers are hard at work to make it work again. But imagine something a lot more dramatic happened. Imagine that we lost the knowledge of how to transmit electricity. This is something totally different. It's not that we know how to make it work again, and that's why we simply can repair it. But imagine for some reason the knowledge of how to transport electricity gets lost. Nothing would work anymore. Without knowing how to transport electricity, even if we could still produce it, we would have no trains, we would have no planes, no phone, no elevators, no air conditioning, no nothing. Our world works because we know what makes it work, and because we can repair things. And that's why the ancient Greeks didn't have radio. Because they didn't know enough about their world. And that's why they didn't even think that radios were possible. And so even though they could make these wonderful little tiny wires in their bracelets, they would never have the idea of turning it around some wooden pole to make it into an induction coil to make it into a radio transmitter. That's what makes us different from the ancient Greeks. And none of this is obvious. Right? If it were obvious, surely the ancient Greeks would have figured it out. It's not obvious. I tried to point it out before. If you have a spinning magnet in front of a coil that gives you electricity, and that magnet is nothing but your fridge magnet, it's wild that this works. Somebody has discovered it, but what made them even think that something like that is possible? Like it's an absurd idea if you didn't know that it works, and if you haven't seen it yourself. How wild is that? You turn a fridge magnet, you power your hair dryer, and you can dry your hair. It's amazing. Similarly, it's not obvious at all that electricity travels along very thin metal wires that go over hundreds of miles from here to the power station. It's not obvious that electricity doesn't travel as nicely through thick wooden poles that hold up the wires. It's not obvious. It's likewise not obvious that if you take electricity that oscillates very, very quickly and you put it into a wire that just ends, that the electricity wants to keep going, but because there is no wire, it keeps going in the air as radio waves. So It's not even that electricity likes to travel through thin metal wires. Sometimes electricity also likes to travel through the air. But why does that happen? And how do I make it work? It's not obvious. And then lastly, you have these blocks of black, weird-looking rocks that you can hold in your hand. And if you put them together in the right way, suddenly they get warm. And suddenly you can boil water with it. Then you can make electricity of it. It's wondrous that that works. It's wild. And my point is that none of those things are obvious, but all of those things had to be discovered. And in fact, if you go back to that situation with the wall outlets and those 60 hertz of electricity, if you're wondering why that unit, hertz, sounds a bit weird and unfamiliar, then that's because it's the last name of that gentleman, Heinrich Hertz, who was a German physicist in the 1800s. And it was him who experimented with very rapidly oscillating electricity. And he stumbled, literally, into that phenomenon of having very rapidly oscillating electricity go into wires that are not connected to anything. And he would be there on the other side of the room with another wire that also has a gap in it, and he would observe sparks, electrical sparks, across that gap in his wire. And he would wonder, what on earth is going on? I have a spark over there, and I have a spark over here, but there is air in between. Okay, and here you can see, this is the first antenna that he built, and exactly the one that I pointed out. It's just two metal wires and two metal blobs on the ends. And you can see there is the induction coil that he used to send that rapidly oscillating electricity into his antenna. But then, you might be wondering, where did he get the electricity from? What did he use to power his apparatus? And you would point out that there is something on that small table in front of the device, and you can see, in fact, wires going into the rest of the thing, and that's a battery. And that battery gave him a source of electricity to use. Did he invent the battery? No. Where did the battery come from? In fact, we get another hint. If we go to our battery in our cell phone or in our TV remote, and we see that unit volts that I pointed out, that might also sound a bit suspicious to you, and that's in fact because it's the last name of this gentleman from Italy, Alessandro Volta. He was the first to invent a battery. Almost 100 years before, Hertz used it to generate that rapidly oscillating electricity that gave him the waves. And in fact, in this painting, you can see he was so proud of his invention that he even put the battery here in front of him on the table when he let himself be painted. But why did he build the battery? What made him invent the battery? Why did he even think something like this was possible? It was because he was having an argument. And he was having an argument with this gentleman here, Luigi Galvani, 10 years before, who is also from Italy. So, the two knew each other, they were collaborating. And Galvani, he was an anatomist. And he studied the anatomy of frogs. You can see a frog there that he is examining, suspended from that metal railing that he had on his rooftop garden. And what he would notice is that for some reason, there seems to be a source of electricity connected to the frog. And so he imagined that the frog itself, animals, are some source of electricity. And that's what he widely talked about and he widely published. And that is what Volta was vehemently opposed against. He said, that's not true. In fact, I can make something that doesn't have any living parts, that has no frogs, no nothing, and it can also generate electricity. And that's why you're not right. And his demonstration is there in front of the table. His battery was a means of proving that Galvani did not have the full picture. Because in fact, you could make electricity without any living beings involved. You just need a pair of metals and some water or some acid or some of that gray goo paste that we saw before. So you can see, any of those discoveries, they didn't come out of a vacuum. All of those discoveries happened within the context of a much wider picture. Heinrich Hertz was able to experiment with these rapidly oscillating electricity because he had a reliable source of electricity. And that reliable source of electricity was provided to him by Alessandro Volta, who invented it a century before. And we just saw that Volta was pointed to that entire effort just because he wanted to prove wrong the viewpoint of Galvani. And so over centuries, this is what happened, and this is what led us to live in our modern world. And today we are in this wondrous and weird position that we totally mix up science and technology, right? We just saw it. If we just, naively ask, where does the electricity come from that I'm using out of my wall outlet, eventually we're led down to the existence that atoms are there. And that atoms have this weird property that if I make them fly apart, they would generate heat, because there's stuff coming apart at very, very high speeds. And so my answer to you of where the electricity comes from involves words like atoms, uranium, which is what these pellets are made from, and the fact that the atoms are 1,000,000 billion times smaller than a foot. Okay? And then there's batteries. But imagine that if you had lived even 200 years before today, even the word electricity might not have been familiar to you. What is electricity? And then, in fact, if I told you that electricity is what you get if you take atoms, the size of 1,000,000th of a billionth of a foot, and so on and so forth, you wouldn't believe me that atoms exist, because how on earth could I know that something, 1,000,000 billion times smaller than myself even exists? Right? It's wild. But all of this was once cutting-edge science. Today we have technology that uses all of those things, and we casually talk about it. Oh yeah, we split the atoms, and that's what makes stuff get hot. But all of this was cutting-edge science. In fact, at a point, people were wondering how many kinds of electricity are there, right? I mean, I made it sound obvious, I hope you didn't buy it, that the electricity in the wall outlet was the same as the electricity in the battery, but all that I used as evidence was that, okay, both are measured in volts, and one was sort of 80 times more than the other. But it doesn't really say anything, right? How do you know that the electricity in your battery is the same as the electricity in your wall outlet? It's also not obvious. People had to discover that that's the case. And we'll see, in fact, how they discovered it. And then you say, fine, okay, maybe you believe the story that I just told you about how that wall plug electricity comes from. It comes because atoms are split apart and they get warm and so forth. And if you believe me for a second that matter, or uranium at least, is made out of atoms, then surely you will have the question of what is electricity made from? What is the atom of electricity that seems to be flowing through very, very long wires so effortlessly to reach me in my living room? And then maybe I gave you an answer, and maybe that answer even satisfied you. I hope it wouldn't. You would ask, okay, fine, now I know what the atoms of electricity are that go into my radio antenna, but then somehow something continues, and that something is clearly not the same kind of electricity you just told me about, it's something else. So what is it that radio waves are made of? Okay, it's another non-obvious question. Okay, then maybe I would give you another elaborate answer, and maybe that would satisfy you. We'll see about that. But then you have another question. You come back to me and say, fine, okay, maybe I believe all of what you just told me, but you also told me that you get all of that electricity, no matter what kind, by boiling water, by making steam, and by turning the turbines and so forth. And you ask me, okay, I mean, what is even different if I heat up water? Okay, you take some cold water, you heat it up to make coffee. Something clearly changes, because if you put your finger into a hot mug of coffee, you'll burn yourself, it'll be unpleasant. Whereas the same doesn't happen if you put your finger into cold water, it comes out of your tap. So something is clearly different, but it's also still clearly water. So what on earth makes hot water be different from cold water? What is heat? It's another non-obvious question. But having such non-obvious questions and trying to come up with answers and then seeing what those answers imply, this is the rough answer of how we got here today. And we saw part of that story already. We saw how Heinrich Hertz and Alessandro Volta had this very wonderful symbiotic relationship, because Heinrich Hertz could use Volta's battery to make his experiments. And had Volta not invented the battery before, Hertz will never have had the chance to even think about or demonstrate the existence of these radio waves. So without a stable source of electricity that was provided to him by his ancestors, he would not have had the chance to progress. And so there is this wonderful cycle, this dance between science and engineering that keeps the world going. And we just saw part of that story. Volta discovers the battery as an act of science. He wanted to prove a point wrong that was made to him by Galvani. And the battery was his way of proving that point wrong. But then, what was once a scientific discovery very quickly became a tool of technology. And in fact, batteries were very widespread among the academics of the time because they were a convenient, reliable source of electricity. And that's also what Heinrich Hertz used as a basis to do his experiments on very quickly oscillating electricity. And so the cycle continues once Hertz figured out that there is something that would eventually be called radio waves. At the time it was called Hertzian waves. This is why today we have mobile phones. Okay, it's this cycle of understanding what is going on outside in nature, understanding natural phenomena, that turns into new scientific instruments, the battery from a purely academic adventure into something that could be used as a tool to the kind of technologies that we have today in our marvelous world. That's the answer of how we got here. The reason why we managed to get that far is because the world has that wonderful property to it that lets us understand something about it without having to understand everything about it at once. Okay, it seems obvious, but it's not obvious. And maybe by the end of this 8-part lecture, you would agree with me. But we can, for some reason, answer the question of what changes when I heat up cold water to make it hot water and eventually steam. And I can even conceive of something as a steam engine to make it useful, to do practical work for me, to pump out water from a mine, for example, without having to know about the existence of atoms. Right? Even though the water and the steam engine and everything else is made of atoms. For some reason, I don't need to care about that for me to answer these questions usefully. And in fact, that's one view of a much larger phenomenon that we also, went through today. If there's a large, complicated thing that seems mysterious to us, like where does the electricity come from in my wall outlet? Well, if it's not clear to you what's happening in that big, complicated, mysterious thing, try to open it up and try to see what's inside. What are the parts that make it work? And then, look at each part individually to see if maybe you can learn something from that. And then, continue on like this. This is what is called reductionism in the world of philosophy, and this is a key aspect that made that circle keep going over and over again. And so this is why and how fundamental science managed to change the world. And this is why today we live in the world that we live in. And so for the next 7 lectures, I want to tell you the same story again, but in a lot more detail. Okay? So we are going to go back centuries to see what actually happened. Because the best people to tell that story, of course, are the scientists, are the people, are the engineers that were actually there when all of those discoveries happened. So we're going to look over their shoulders to see what they were thinking, what their labs looked like, what the kind of context was in which they were operating, and we're going to experience how those discoveries came to be. And so in the first part, starting next week, we're going to go after one of those questions, those seemingly stupid questions that I just posed to you. What is the nature of heat? What happens if I heat up water? And what does that tell me about steam engines? Can I build a steam engine that works very, very well? And we're going to start that story by figuring out how people discovered that there was something that today we call temperature, and how people built instruments that can measure temperature, and how these instruments became more and more elaborate, and how temperature measurements turned out to be a precision science at some point, a state-of-the-art precision science. And then how, being able to measure temperatures very, very accurately, people discovered that they could build steam engines. And about how, just looking out, watching snow melt in the spring, we learn something very, very deep and fundamental about what heat is. Just being observant to nature around us. Then we will see about, fine, we have steam engines, but is there some trick? What is the best possible steam engine? Does it run on water? Does it run on something else? What do I need to do to make it work as best as I possibly can? Then we're going to see what cannons and the boring of cannons has to do with heat. And then eventually we'll end up where we started today, which is the generators and steam turbines in a modern-day power plant. In the second part, we're going to go after another one of those stupid questions, which is, what is the nature of electricity? And how on earth can I send signals through the air over large distances without a wire? And that story is going to also start, ironically, with the ancient Greeks, and with amber, which they had for a very long time, and with magnetite, another mineral that they had known for a very, very long time, and it was very mysterious to them. And we're going to see how people built the first reliable sources of electricity and why they resorted to spinning around glass globes like this. And then we're going to see how people discovered that they could actually have wires transmit electricity instead of poles of wood. What was the discovery like then? What were the people like that made the discovery? What made them think and what made them do these experiments? Then we're going to see how electricity was a party trick at some point, the party trick of the rich people, the kings. But we will also see how very quickly that party trick turned into a frightening and terrifying discovery. Then we're going to see how, at some point, it seemed to be very confusing because there is different kinds of electricity. There is animal electricity, and there is the normal electricity, and there is whatever, Volta's electricity. There is different kinds of electricities that are all produced in different ways, and everything is very, very confusing to everybody. But then finally, everything starts to make sense, and everything will be unified in some common understanding, and there's only one kind of electricity. And then finally, we will see how that discovery that there's only one kind of electricity led right on to the next question of, what is the nature of matter? Are there really atoms? If so, what are the atoms made of? And we're going to see how the pursuit of that question eventually led to cancer treatments in the modern world. But the story is going to start again with electricity. People were very fond of electricity, and they tried to run electricity through everything, and they also tried to run electricity through gas in a glass tube. And they would discover, by chance, that there is X-rays, that you can actually make medical images like that by running electricity through gas. We will then see that there is also, a different kind of X-ray that you could make without running electricity through gas, because it would be naturally produced by certain types of rocks that you would find around you. Then we will see how the physicists were very confused and they didn't know how to continue, but it was the chemists who rescued the day. It was chemists who got a lot of hints from their own work about what makes different elements be different. And then we'll see what all of that has to do with a very common British dessert, a plum pudding. And what this power couple here, the wife and husband dream team, had to say about chemistry and physics and radioactivity. Then we'll see how the development of new instruments, new and different ways and improved ways of looking at the world helped the people to make progress. And about how pictures like these eventually led to the discovery of a new constituent of atoms that people didn't know about before. We'll see what this group of gentlemen in Italy that named themselves the Via Panisperna Boys had to do with this device that eventually was erected right out of this building here on the other side of the street, the Chicago Pile 1 and the first nuclear reactor. So how did all of this come together? If you're curious, you can come back next Saturday, same place, same time, to hear more. Thanks very much. Questions? Go ahead.
I wonder if the Chinese or others have any non-Western stories about the origin of all this science.
Very good. So the question was whether other cultures, non-Western cultures, have their own history of science, and to what degree it's different from the Western history of science. And the answer is, there was a lot of parallel discovery. At the beginning, different cultures were very sequestered, and they didn't necessarily speak to each other much, and there were multiple rediscoveries of the same concept in different cultures of the world, absolutely. As science got more and more globalized, and as scientists across the world started speaking to each other a lot more, that sort of happened less and less and less. There was still a bit of that during the Soviet Union, where there was the Iron Curtain, and there was not a lot of exchange between the East and the West. But even then, people tried to find ways around that, and then people tried to speak to each other. Because as we saw before, serendipity and just the sheer chance of talking to each other can sometimes be very, very important. And in fact, we're going to see some of those hints of what the Chinese were thinking about magnets are going to show up in a couple of lectures from now.
Yes, you talk about the interaction of technology and science, and I'm sure you know that this is true, but it's not all one way. It's not science makes discovery, which is immediately. And in fact, there's a very old cliche almost that science owes more to the steam engine than the steam engine owes to science, because thermodynamics was developed by people who were trying to understand how steam engines work, what the most efficiency was.
That's right.
And if you go way back further than that, there are technologies that were developed without what we would call science. For example, smelting, this is getting away from, smelting of iron, for example, was discovered clearly because you had to have very high temperatures in a reducing atmosphere. And how did that happen? Well, the only way it could have happened was in pottery kilns. And so it was an accident because people were dyeing the pottery with ores that gave different colors. So they were changing the reducing atmosphere, and they were getting the heat very hot. So that is how, in antiquity, smelting was developed, and it was developed in 3 separate places independently. It was developed in Africa, it was developed in Europe, and it was developed in China. So that was not from, science, first discovering the science of chemistry and then going to that.
Perfect.
And a third thing.
I'm going to remember all of that.
We don't know, so much has been lost in technology. And there are things, for example, what's called the Baghdad battery, which was probably an ancient battery going back, we don't know how to date it exactly, but probably roughly between 200 BCE and 200 CE. That was, we don't understand why, this was apparently a battery, but the suspicion is it was made, they had discovered that you could electrolytically plate things with, this battery. So there are lots of technological discoveries that could be made without prior science.
Perfect comment. So the comment was made for the record that this sort of cycle here is just one side of the coin, and it's a bit oversimplifying the story, and I agree with you 100%. And in fact, we're going to see, as we follow along some of the characters, there's different kinds of scientists and different characters of scientists, and we're going to see different individuals that had very, very different approaches to things. There were people, for example, who just went out there and played with things, and they stumbled upon a chance discovery, or they just tried all the possible things that they could try, just out of sheer curiosity. And they sort of accidentally made a discovery, but maybe they didn't even realize that they had made a discovery. And then there's other people who were very, very systematic about what they were doing. They knew exactly what they were after, they knew exactly what the kind of variables are that they could play with, and they just, pursued and persevered and eventually made it to there. So there's different approaches to science, and there is no clear boundary between where science stops and engineering starts, but all of that is going to be necessary as an element in that story. And we're going to see exactly what you pointed out going forward. Thanks very much.
So going back to your example of the induction coil with the spinning magnet, we're used to thinking of the magnet having a magnetic field around it that surrounds and is outside, exterior to the magnet itself, so in the air, let's say. And when you spin it, you're changing the polarity, obviously. And so something is moving through the air that reflects that change of polarity.
That's right.
And my question is, are the properties of that change of whatever is going on in the air, are they strictly magnetic as opposed to electric? Do they have the same character as the electromagnetic waves that we think of as flowing from the radio antenna, or is there some difference? In other words,
Right.
Are those radio waves there, or is it something
Wonderful question. So the gentleman here was asking, he was trying to give an answer to what happens here. I called it wild, but he says there's obviously something that is external to the magnet, and he called it a magnetic field, which is one term in sort of in a lexicon of terms that people are using today to describe what's going on. And he was asking what sort of the nature of that magnetic field is, and how it, for example, is different from the kind of magnetic or electric phenomena that you have in a radio wave. And the answer is, as we know today, this wasn't obvious, by the way. The concept of a magnetic field came very, very late in that entire history. But we know today that there is, strictly speaking, no difference between an electric field and a magnetic field. So something that looks purely magnetic to you might actually look like a mixture of electric and magnetic phenomena to somebody who is sort of walking past you and sort of is observing what you're doing. Okay, so different observers in different states of observing the same object, the same phenomenon, will have different descriptions of it. You might say it's purely magnetic because I'm just looking at this magnet spinning and I just see a magnet, whereas somebody who is in a plane overhead will also perceive that there is an electric component to it. And that's why we call it electromagnetic waves instead of electric waves or magnetic waves, because it's always both that contribute. So they already contribute here, although from your perspective it might seem like it's only magnetic, and from my perspective it might seem it's a mixture of the two. It's always both, to different degrees.
What ignites the pellets in the uranium when they're in a rock? What about?
Great question. Okay, let's see, where's the uranium? So the story I told you is that once something ignites, once one atom splits apart, you get a chance to also split another atom, because you get sort of this residue, that sort of little yellow dot here that can move to another atom. Okay, that's the thing that keeps stuff going. But as far as I understand your question, you were asking, why does the first eruption happen? Is that right? The first eruption, believe it or not, happens by chance. There's so many atoms of uranium in even that tiny little pellet here, and even one of them, that there is a non-zero possibility of something, of one of those atoms splitting apart by coincidence, by chance. And if you don't like that answer, then you're in the same line with Albert Einstein, who said that God doesn't play dice. And he really opposed that viewpoint that things could happen by chance and by accident. But as far as we know, that's the answer.
So uranium in the ground is harmless? It's not radioactive?
So it's very good question. So the question is whether this kind of uranium that this gentleman here is holding in his gloved hand is sort of related, or to what extent is that different from the uranium that you find in uranium ore, for example. And the answer is that this is a sort of purified form of uranium, because uranium ore is very, very rarely super pure in uranium. It's got all kinds of other minerals in it that you don't necessarily want to have in your fuel pellet. So you've got to refine the uranium out of that, and you've got to remove all of the residue that's not what you want. So that's what you do. Yes?
It'll be interesting to see how you cover self-censorship. Not all ideas, not all discoveries are vibrantly or eagerly received.
Right.
There's a lot of rejection.
Right.
It's like doing a thesis. You must defend your thesis or
Right.
defend your dissertation.
Right.
It'll be interesting to see how you cover that.
We are going to see that a lot of the important discoveries were actually made by people who were not embedded in the academic community. Okay, these were, you would call them today, amateur scientists, people that were just experimenting away, at night in their basement or in their homes. They were trying stuff themselves. And then they would discover something that the establishment, the academics who were working at universities had missed. And then it depends very much on, we're going to see examples of both sorts. There's going to be people, amateurs, if you want to call them that, although that has a bit of a sort of negative connotation to it. I mean, amateurs in sort of highest possible regard. We're going to meet people who made such discoveries and who managed to get them heard, to make other people aware of them, and to make other people try to reproduce what they found. Because ultimately, that's what you need to do in order to convince somebody. They need to see it for themselves. On the other hand, we're also going to meet people who, by bad luck, were living in very remote places. that were, out on the countryside with no universities around them. And there were also people like those who made important and big discoveries, who even maybe recognized that they were important discoveries, but who couldn't sort of be heard in that same way because they didn't have access to the establishment to sort of spread the news. And in such cases, more often than not, it would happen that the same or related discovery would be made later or almost simultaneously by somebody in the universities. And then, in such cases, unfortunately, history is rarely fair, and it would be the wrong person who would be credited with the original discovery. Absolutely. And we're going to see, some of those examples as we continue. Yes?
That was my question, what you just touched on, when the gentleman talked about the three independent cultures inventing a similar concept like smoking. Do human brains think at the same time? They were thinking independently, or are some cultures more curious than others? Or, like you said, in the middle of nowhere,
Yes.
same idea
Yes.
came up at the same time.
Yeah, so the question was sort of related to what we just discussed. Is it the case that some societies and some cultures are sort of more prone to making discoveries than others? And I think that's a question that's sort of very difficult to answer because it depends on many things. But as we're going to see, in many cases, chance really plays a big role in making a discovery. And sort of I would hesitate to say that, there's certain cultures that are inherently more lucky than others. Right? So discoveries can happen, anywhere, right? And whenever. Yes, please.
When you were describing the fission of uranium, you were saying that the decay particles are spreading out and causing friction, and that generates a lot of heat.
That's right.
That would be, if I remember right, that would be barium and krypton.
That's right.
But wouldn't there also be a lot of heat generated by the fact that you're unlocking the strong nuclear force, which originally got those protons together because they're the same charge, which also are the same charge together.
That's right.
And so maybe the heat from the original, say, supernova explosion, which would have been 16 billion degrees, is locked in there, and that gets released.
Right.
Also, wouldn't that be the predominant heat source?
Very good. So the gentleman was asking about, the precise nature of heat here. So I told you that, these two elements, barium and krypton, that sort of are the remnants of that original atom, that nucleus of uranium. As they move apart, they have friction with the rest of the material, and that's what makes it hot. And the gentleman was right in pointing out that these two halves of the uranium nucleus, even though they might be sort of speeding apart from each other at one moment, were previously tightly bound together in that same nucleus until that neutron comes around and hits it. So is it really the case that that friction is sort of the sole source of the heat, or is it not some nuclear physics phenomenon that releases that heat? And he mentioned the strong nuclear force, which is sort of a concept of force that keeps these two halves together before they were sort of splitting apart. That's our understanding of what happens. The answer is that yes, there is a strong nuclear force that keeps things together, and yes, it's a strong nuclear force that sort of fails to keep the halves together once the additional neutron comes in. But the way in which that energy that the strong nuclear force stores is released is precisely by means of the energy of motion of those two barium and krypton nuclei. Okay? So if there wasn't a material around, if this happened, let's say, in vacuum, okay, without air, without a material around them, what you would have is no heat. You would really just have those two elements flying apart at insane speeds. The heat comes about because there is something around them to stop them. And because they are stopped, they will then transfer that energy that's contained in their motion to whatever's stopping them, in this case the other atoms of uranium, which will then make those atoms vibrate, and that's what we perceive as heat. Okay, and you will see, I just used a lot of concepts that I didn't properly introduce. Energy, vibration, heat, and so forth. And I made it sound as if, vibrations of something is what we perceive as heat. And in fact, this is what our current understanding is of what heat is. But as we're going to see next time, it took, many, many steps to get to that insight. Right? If I'm touching this table and I feel that it's warm, it's because that table is sort of vibrating imperceptibly. And that's exactly what those nuclei of barium and krypton are doing. They're making the rest of the pellet vibrate, and that's why it gets hot. Yes, please.
Well, first of all, anybody who's interested in the topic of why some civilizations advance and others don't should really read that book, Guns, Germs, and Steel, which actually deals
I've
with
heard of it.
exactly that question.
Right.
But what I wanted to point out is the slide that you had that said you don't have to understand everything to understand something.
Yes.
Because it's my understanding that the ancient Egyptians did electroplating and that they used wires, even though they didn't understand what was going on behind it. In fact, there are people who believe they actually use solar energy in addition. But what interests me, or I find fascinating, isn't just the progress of science, but the opposite, is how we end up losing great scientific knowledge over long periods of time, or science that just stays flat with nobody picking it up and investigating it or advancing it.
Right. So for the record, the gentleman was pointing out that there is a book called Germs and Steel, which people should read, also people who would watch the recording should read, because it talks to some of those some of those topics and about how different discoveries sort of interplay and intermingle. And his comment was about the opposite of what I was sort of describing, which is the stagnation of science or the absence of interest in a certain branch of science, or in the worst case, sort of the loss of knowledge that has once already been achieved. And unfortunately, this is also something that can happen and that we're never sort of really protected against. And in fact, there is also some people who are worried that something like this might happen again, even in modern times. So it's not that it's not even that all of the miracles of technology are sort of to be taken for granted, but it's also not to be taken for granted that we will have technology going forward, right? It could all disappear again if we decide that we are not interested in fostering and pursuing that branch of knowledge. Unfortunately, there's nothing to be taken for granted. It's all up to us to keep it like this and to make it going. Nothing happens on itself. Okay, if there's no more questions, thank you very much.